So good afternoon, and everyone. Welcome to this session of the Lisbon Philosophy of Physics seminars. This series of events is organized in the context of activities of LANCOG Research Group, which is based at the University of Lisbon. In this series of events, we're going to speak about the foundations and philosophy of quantum and space-time physics. As is usual, in these seminars, we will employ standard Zoom etiquette. So please switch your microphone off while the speaker is talking. Each session will be divided in two parts. In the first, Peter will deliver his presentation, and after a short break, we will have a Q&A session. Today is a real pleasure for me to introduce our speaker, Peter Morgan. Peter has a degree in mathematics obtained at the University of Oxford in 1978. Then he worked as a computer programmer, and then in 1993 he received a master in particle physics from Durham University. His work is mainly focused on the foundation of classical and quantum mechanics, and he wants to understand the relationship between quantum fields and classical random fields. He interacted a lot and for several years with the philosophy of physics groups at London School of Economics and in Oxford. And since 2004, he has a lab associate position at Yale University. He developed his approach to measurement theory in recent papers in Physical Scripta, Annals of Physics, and Journal of Physics A. But without any further ado, I would leave Peter the stage. So please go ahead.
Thanks, Andrea. So I'm going to start with a rather empiricist, operational, and even Copenhagen-y kind of approach, in which really we have a device in our hand and we're content with that. And we'll attach an oscilloscope to it, and we'll see that we have a noisy signal coming out of that device. And occasionally we'll see events will happen where the signal level increases, and we'll register the time of that as data and save that to a computer memory. Now, as well, the noisy signals, I'll argue, we can think of those as embedded in noisy surroundings, which will, because of the noise, will require moderately sophisticated mathematics, more sophisticated than we're used to using for ordinary classical fields. So then I'll apply some of that thinking to a particular experiment in which the Bell inequalities are violated. So out of that, I'll argue that non-commutativity is necessary for classical mechanics to be enough to describe the violation of Bell inequalities. And I'll also add in quantum noise. And I'll mention as well how analyticity needs to be discussed, and I think needs more attention than it has been given in the past. So having added non-commutativity into classical mechanics, I think we have a measurement problem for classical mechanics. And I'll discuss how I think we can make that less of a problem by thinking in terms of joint probabilities. Now, everything is focused towards generalized probability, and I will argue just in one slide that we can think of that as a way to discuss intervention and causality. Now, I have something of a simple-minded approach to quantum non-demolition fields, which I'll explain in a moment, which I try to take a signal analysis point of view to that. So I'll use words such as modulation from the signal analysis literature and so on. And then signal analysis approach again will come in as a way to rethink interacting quantum fields. So this schematic is obviously incomplete, but I take it that we have many devices, each of which is in contact with whatever it is that is contained by the experimental apparatus. And from those devices, we have signals, which then are processed by hardware into digital data, which is then recorded. And then days or years later, we apply whatever analysis we're going to do to that data, which gives us supplementary information, more processed data, and we'll write a paper that describes how we performed the experiment. Now, at first, that obviously sounds quite operational, but by the end, I intend and hope that you'll see that there's quite a realist perspective here as well. Now, we have a quantum theory framework, and to that, I want to add something that looks like signal analysis, looks quite classical, but isn't, to describe the same experiment. But just because we have two different experiments makes the experiment no different. The data you get out just comes out the same. Nonetheless, having two different theory frameworks or more allows you to consider what experiment you would want to do next rather differently. And so your choice of what experiment you'll do next will be different. A signal analysis and data approach, I think, is well suited to machine learning, which puts us into the philosophy of computing, where I want to give a shout out to this article that just turned up only about a week and a half ago. Now, raw data is something that people sometimes say, but I want to say that raw data is never completely raw. We could call this raw data, but it's only a shadow of the raw signals, and the raw signals are only a shadow of the raw whatever it is that's in the experiment. I want to emphasize that for me, everything is about models. That's the way I approach science. And particularly my models are always wrong. Yours may be perfect, but mine are always wrong. And quantum theory, however, as a framework, I think really does not need any change. So to look at a few quotes from Bohr in 1921, he says that the classical theory of electromagnetism, well, it's not much more than a natural generalization. But of course, 2 or 3 years later, all that falls apart. And he's left saying in 1949 that the accountable evidence must be expressed in classical terms. But the phenomena themselves transcend the scope of classical physical explanation. But the same year, Dirac is saying, well, let's change classical mechanics. Let's play a different game there. Very much, well, leaving that aside. Okay, so Bell says something very similar in his article, The Theory of Local Beables, where he says observables must be made somehow out of beables. Now, I'm going to read that as saying we should be changing classical mechanics, although I suspect that's not what he meant. And I'm going to use the Poisson bracket to make new observables. So in a sense, that's the opposite of adding hidden variables to quantum mechanics, which is what most of the research in the last 100 years has tried to do. Now, this last quote serves a different purpose. It's Bell's polemic against measurement, in which he admits, however, that experiments have results. Now, I think it's operationally okay, nonetheless, to say that we can collate parts of an experimental data set into multiple measurement data sets, depending on which device the particular piece of data came from and according to what the analysis that was applied to it. But I'm not going to think of that as measurements of particle properties. I think that is, well, my reading of what Bell was railing against at that time. So I do want to take quantum field theory and signal analysis both as grounded in actually recorded measurement results, which are about the noisy signals on the signal lines, and which indicate something about the device's surroundings, whatever that is. And we take quantum field theories to be our best theories, but we very often still take particle properties to cause events. But I want to suggest that we hesitate before mentioning particles or systems or tensor products or particle properties. And I also want to suggest that we should hesitate before mentioning a field that is measured. Because I think the mathematics of quantum field theory is very clear that what we have is a field of measurement operators. And so it's not a field that is measured in the mathematics. Now, finally, for this slide, we should keep very clear that quantum noise is very different from thermal noise. For an engineer, shot noise is handled and dealt with in a very different way than thermal noise. And I'll discuss that later. So if we have devices giving us signals and events and data, then what do we have to do to get ourselves particles? We have data about millions of events. We have to write algorithms to decide how to assign each event to a particle. We can't work on an ad hoc basis with millions of events. So if we have an algorithm that, given these 5 points, says, that's one particle. If later we see 2 more events, and those are also reported, and the algorithm then has to run again, it will then say, well, what is this event? Is this caused by this particle, or is it caused by this particle? Or did this event only happen because both particles happen to be in the same place at the same time? So I suggest that events to particle algorithms, they're global, non-local in other words, after the events, and they're quite fragile in some circumstances. Of course, sometimes it's very clear that there is just a single line there. On the other hand, signal-to-events algorithms, which are often implemented in hardware, they are non-Markovian in this case, in the sense that we have to report events only once. So when an event happens here, we could be reporting events multiple times through here. So we have to remember that we have reported event already. That indeed is non-Markovian algorithm. But nonetheless, this is less fragile and non-local than the events-to-particle algorithm, because if we add these two events later, that doesn't change any of the information about these as events. It only changed the particle property assignment. Now, finally, before I talk about the Bell inequalities, for quantum mechanics, we have measurements which we might label M1, M2, M3, and so on. But in order to be able to describe the experiment to some other experimenter, we have to have descriptions that correspond to each of those measurements. So we could write this as description 1 measurement, description n measurement, and so on. Now, in quantum field theory, we have an idealized form of that, in which we use smearing functions defined on Minkowski space, particularly for quantum field theory, or what in mathematical physics are called test functions, where we smear an operator-valued distribution, m of x, to give us what I'm going to call an F measurement. So an F measurement is the operators we're going to work with. And we might have many, in which case we have F1 measurement, F2 measurement, and so on. And I think of these smearing functions as descriptions of how a measurement is different from point-like, because point-like measurements just don't happen in the real world, nor in the theory. So for quantum field theory, we have the F measurements commute with G measurements if the functions F and G have the supports of those functions are causally separated or space-like separated. Whereas for what I'm going to call a quantum non-demolition field theory, a QND F measurement always commutes with the G measurement. And that's what I've called in the past a random field theory or a classical random field theory. And I'll show you later how for quantum optics, we can construct an isomorphism with an appropriately constructed quantum non-demolition field theory. So this is an experiment that was carried out in the mid-90s by Gregor Wyss. This is the schematic from page 60 of his thesis. And I like to work with this partly because the schematic is so beautifully suited for what I want to say. So when an event happens in an avalanche photodiode and the signal change is detected, then the hardware records only the time at which the event happened. It records which of the two avalanche diodes registered the event, and it records what the setting was to the electro-optic modulator at the time. At the same time, Gregor also has a nice little feature here, which he talks about the central apparatus pumping whatever it is within the apparatus. He doesn't talk about injecting one particle, which then gets split into two particles. He just talks in an almost field theoretic way. Pump, I will say, modulates. So of course, this compressed record, what we've stored here, doesn't let us analyze any other signal details. And indeed, to record everything would require millions of times more data, and you really would be into big data computing. So very quickly, some words about an avalanche photodiode. It's made from exotic materials that are processed exotically, is subjected to exotic bias conditions, and most of the time, it just burbles along while it interacts with its surroundings. But sometimes it gets cross, and then we record an event, time of an event. And of course, that's more interesting than if this never happened. So this is the kind of apparatus we seek out and we use. We don't use rocks. Then an APD's electronics calms it down, so it can burble again, so it can report a new event, and we can start to do statistics. Now, an APD, if you put it in a dark room, will nonetheless show events. But then if we put in some lights and some mirrors and other APDs, then we'll see the statistics will change. And if we look closely enough at the statistics over a long enough period, we should be able to tell quite clearly what else is in the room. An APD, however, tells a story even when it's not crossed. So we could, if we were smart, look at the signal here and make an educated guess as to whether an event is about to happen. And indeed, people have done that. Finally, for this slide, an APD's frequency scales are there's 15 orders of magnitude between the optical scale at 10 to the 15 hertz, 10 to the 9 for electronic, 10 to the 6 for the thermodynamic of when there are events. And for us, of course, we operate our heartbeat at 1 hertz, more or less. So we hope to learn something about this by recording just this. And I suggest there's very much room to go for big data and to at least record things at the electronic scale, much record this, in other words, and analyze it. So when Gregor runs his experiment, this is a 10-second period in which Alice sees almost 400,000 events, and this graphic shows 15,000 of those events, precisely when and where those events happened. And when Alice and Bob both record an event, more or less at the same time, the majority of them in this color scheme are green or yellow, which is to say that they are off the central diagonal, the blue and the red. So given this 15,000 events, we're going to apply an algorithm to it, in which the first thing we can do is we can collate the events by the relative timing information, which gives us these 16 different histograms, one for each for the different APD settings and the electro-optic modulator settings. And then we can add up those numbers in the histogram to give us these 16 numbers. We can take those 16 numbers and put them into the more or less standard calculation, the CHSH calculation, and out comes a violation of the Bell inequalities. So that violation has come from completely classical data, processed using a completely classical algorithm, and now classical mechanics throws up its hands and says, I cannot do with this. This is not okay. If we transformed the recorded experimental data in innocuous ways, then I suppose we could have used commutative algebras to model the algorithms we've used on that classical data. But in classic quantum mechanics, we model the violation of Bell inequalities using non-commuting operators. And of course, in classical mechanics, as usual, we don't have non-commuting operators. So without non-commutativity, classical mechanics is computationally incomplete. Quite the opposite of what we usually say about quantum mechanics. So how can we add non-commutativity to classical mechanics? I've told you already, it's the Poisson bracket. Because here I've concentrated on non-commutation, whereas many authors will focus purely on the non-locality. But I do want to say that if the electro-optic modulation was at much lower than the 1 megahertz, we'd have precisely the same data. But that low electro-optic modulator rate really won't probe non-locality. But on the other hand, for quantum fields, non-locality is closely associated with measurement incompatibility. So I don't want to downplay the issue of locality at all. So last slide before we move on. At a fine-grained scale, Gregor's experiment is not at equilibrium because clearly there are events happening every megahertz, and those are thermodynamic transitions. But at a coarse-grained scale, Gregor's experiment is at equilibrium because if we measure a particular 10-second time period and a different 10-second time period, we expect to see the same violation of the Bell inequalities as a thermodynamic fact about the experiment. And so it's time translation invariant. So it's equilibrium in that sense. And to me, thinking of quantum mechanics and indeed this experiment in a thermodynamic way makes me much less worried about whether this is non-local or local, because we expect for thermodynamics that boundary conditions will determine what the equilibrium state is. But if we have an experiment, this experiment, in which we do not have equilibrium, so when we first turn on the power, then there'll be a slight delay, and then the event rate will increase in each of the 4 APDs, and then also the coincident event rate, there'll be a delay, and then that will also increase. And the same for the violation of Bell inequalities. But will those rates be exactly the same? Or how are they different? And how do those rates change at different distances? And just generally, there's a whole slew of things that you could consider. And these rates are technologically important because sometimes the power has to be turned on. And you want to know how soon you will have the violation of Bell inequalities that you're going to use as a computing or other resource available to you. Now, to me, it seems to me that some experiments make more sense as signal analysis than as probes of particle properties. We're just going to hesitate. There may be particles there, but we're not going to assume that too quickly. So before I can talk about classical mechanics, I'm going to first of all talk about an abstract way, an algebraic way to think about quantum mechanics and classical mechanics in a very comparable formalism, in which I'll take there to be abstract measurements, M1, M2, M3, we can add them, we can multiply them, in which linear operators correspond to random variables, and the spectrum of each linear operator corresponds to the sample space of the random variables. And the multiplication can be non-commutative, in which case we say it's quantum mechanics typically, or commutative, in which case we say it's classical mechanics. And then because we want to make contact with quantum mechanics, I'll take it to be associative, distributive, with unit, and so on. That tells us nothing about measurement results. But a statistical state is precisely intended to tell us what expected measurement results go with any particular measurement operator. And that tells us also what the moments of a particular measurement will be, and that extends to a characteristic function and hence to a probability distribution as well. Now, it's standard in the literature, because we want to make contact with quantum mechanics, to have these four conditions must be satisfied by a statistical state. It must be positive, normalized. It must be von Neumann linear, so that even if A and B don't commute, we still have this linearity satisfied. And it must be compatible with the adjoint. With that construction, we can use modulation of that state by taking an operator and bracketing it and its adjoint around the measurement operator we want, the measurement we want to know the results of. And this construction, it also satisfies the requirements for it to be a state. And that allows us to use the Gelfand-Naimark-Siegel construction of a Hilbert space. And now we're sort of in the same territory as quantum mechanics, except we don't have a tensor product, we don't have a notion of particle properties or anything like that. We simply have statistics as they apply to the real world. So the GNS construction also lets us think of a state applied to a measurement operator in terms of a bra and a ket bracketed around a measurement operator, and similarly for a modulated state. So how does this apply to classical mechanics? Classical mechanics is often presented as an algebra of functional and phase space, and there are three binary operations. There's addition, there's multiplication, and there's the Poisson bracket. So this isn't your usual high school algebra. But we can introduce two operations, multiply by W, YW, which just multiplies by W, and Poisson by W, ZW, which just applies the Poisson bracket in this way. And a familiar example of this is Poisson by the Hamiltonian function, which gives us a generator of time evolution, the Liouvillean operator. So we have, as we expect, that multiplication commutes with itself, but Poisson and multiplication does not commute, and nor does it commute with itself. So that generates for us a non-commutative algebra with addition and composition that is a high school algebra. So we can compare it quite nicely with quantum mechanics. And indeed, I suggest we can use these Ys and Zs of something that's more powerful than classical mechanics. So I've called it CM+. And we don't have to use quantization and the correspondence principle and the Ehrenfest theorem and so on to go back and forth between classical mechanics. If all we want is to be able to describe experiment using the tool non-commutativity, and this gives us an algebraic measurement theory that we can say that is indeed exactly the same as that of quantum mechanics, because we're going to operate in a Hilbert space formalism. So to go to a specific example for the classical simple harmonic oscillator, we have the Poisson bracket as usual. We have multiplication by Q, multiplication by P. We have Poisson by P, which is just derivative with respect to Q, and Poisson by Q, which is derivative with respect to P with a minus sign. So we have these two commutation relations, which we are just as we're very familiar with. Then we have multiplication by the Hamiltonian function, and we have the Liouvillean operator, which is this derivation. So if we want a state that tells us the results that we expect in this classical simple harmonic oscillator in a heat bath and interacting with that heat bath, then we go to the late 19th century to the Gibbs thermal state, and I'm going to present it in a generating function form, and I'm going to introduce J as a complex structure so that we obtain as the characteristic function for the probability distribution for the simple harmonic oscillator this. But now we're in a Weil-Heisenberg group situation where we want to extend this state over the Y and the Y operators to also be a state over the Z operators. And that's very constrained, so that we can fairly confidently introduce a raising and lowering operator, just as we do in quantum mechanics, to construct ZP in terms of A and A dagger. And similarly for a B operation, of where the B lowering operator acting on the vacuum, not the vacuum, the KT state, gives us 0 in both cases. So we can construct modulated non-equilibrium states in this formalism, just as we do in quantum mechanics, and gives us a Hilbert space. It's looking very similar. And indeed, we can, instead of mapping a classical Q and P to a quantum Q and P, we can instead map Q and J partially Q and P and J partially P to 2 copies of a quantum mechanical simple harmonic oscillator. But here, crucially, there's a constant in here, KT, that is not H bar. But this is nonetheless about an irreducible noise, because here the Gibbs state does not care what the interaction with the heat bath is, nor what the heat bath is, so long as those things are such that the probability distribution is what we are going to use to model the situation. So what is the difference between quantum and thermal noise? H bar has units of action, whereas KT has units of energy. That's a straightforward difference. But to get a real handle on this, it's just we have to go to quantum field theory, where the quantum vacuum is where we find quantum noise, and that's Poincare invariant. Thermal noise, however, is generated by we need to specify a time-like direction and a Hamiltonian operator in order to construct a thermal state. So this difference of symmetry properties can be used in CM+. So if we adopt that, what we say is that H bar is an amplitude of a classically comprehensible Poincare invariant noise, whereas KT is an amplitude of thermal noise. So this gives us, I think, a new reason to think that we must work with field theories, because we can only define the Lorentz group if we got more than 2 dimensions, 2 or more dimensions. And it also means that H bar to 0 is just a mean field approximation for the Poincare invariant noise. It's not a classical approximation as such. And so I suggest we should stop saying so. Finally, we have for classical mechanics, for the simple harmonic oscillator, that ZH, the Liouvillean operator, is anti-Hermitian. So I'm going to consider JZH, which is Hermitian. And it, we find, doing the calculation, it comes out to be a difference of positive operators, so it's not a positive operator. And that contrasts absolutely with the Hamiltonian operator in quantum mechanics, which is bounded below. Now that being bounded below leads to analytic properties in quantum mechanics that no mathematical physicist is going to want to give up. It's enormously useful. It's used all the time when we're doing the mathematics of in quantum mechanics. So CM+ includes non-commutativity and includes quantum noise. However, I suggest we don't try to include analyticity. So what I think we can now say is that quantum mechanics is an analytic form of CM+. And that gives us something where we have CM+ and quantum mechanics both have the same measurement theory. So since it has the same measurement theory, that led me down the trail that led to this paper, in which I take the collapse of a quantum state to be quite nicely thought of as a joint probability construction. So if we have 2 measurements, A and B, that have these 2 different sample spaces, and we can present them in terms of projection operators in this way, then for solo measurements, with the density operator rho, we obtain the result alpha m with this probability given by this trace, and similarly for the B measurement. But if we do 2 measurements, where we do A first, followed by B, we say that the result alpha m collapses the state from the state rho in using the projection operator associated with this eigenvalue. Then we measure B in that state. So we obtain the result alpha m followed by beta n, and the conditional probability for that we just write like this, and that comes to this expression. So the joint probability is just this without the denominator. And then we can apply the trace property to move this projection operator here. And so we have two equivalent ways, mathematically equivalent ways, of presenting this joint probability, either with the projection operators acting on the density matrix or with the projection operators acting on the subsequent measurement. So we can use the positive operators JMN, constructed like this, to generate joint probabilities. So instead of collapse affecting a state, we can take collapse to affect the next measurement. And this fits very nicely with relativistic thinking, because if two measurement operators are associated with space-like separated regions, there's no effect of one measurement on the other. There's no question of whether the state is reduced or not, because we're talking about it purely in terms of measurements. And we can use the positive operators JMN to construct what I've called the collapse product, measurement A collapse B, which has the sample space A cross B, and that even if A and B don't commute. But since they do commute, since this is a joint probability, excuse me, that's traditionally thought of as rather classical. So we can indeed instead use commuting operators A prime and B prime and a different state rho prime that give the same joint probability. So if in the first model we've used this to obtain a particular set of probability measure, then this will give us the same probability measure because we have plenty of freedom to be able to set that up. And for the mathematically inclined, we can use the Neumark dilation theorem to construct a joint projection valued measure, AB, that has the same, it operates in the same way as A collapse B. And that, however, acts in a larger Hilbert space. So we can think of what we just constructed as a super Heisenberg picture, because we both unitary evolution and collapse are applied to measurements. Schrödinger picture, in contrast, applies both to the state, and the Heisenberg picture applies unitary evolution to measurements, but it applies collapse to the state. And I find this very unifying, because we could also call this the Bohr picture, because it's rather classical, just as he insists on for the experimental results. And also for Bohr, he very often talks about measurements affecting other measurements. And this is a difference between him and Heisenberg that's discussed in a paper by Don Howard in 2004. But we can also think of it as a quantum non-demolition picture or as a consistent histories picture, because it's all commutative. Or we can think of it as the Everett picture. This is pushing things a little further because it's just no collapse. Or as the Einstein picture, because it's rather classical, although whether he would like the way in which I've introduced the Poincare invariant noise is, of course, a larger question. So we're doing signal analysis, though, with this. So we're going to use the collapse product multiple times. And to do that, the only way I've found to do that in a systematic way, instead of in an ad hoc sort of way, is to use the sequential product, in which we take two positive operators and we take the second and we multiply it on both sides by the square root of that. And this is something that Stan Gooder in particular has introduced in the 90s. But this is non-associative product, because you find that if you talk about the A collapse B followed by collapse C, that gives us this expression. Whereas if we talk about A collapse followed by B collapse C, we obtain this rather simpler expression. So we may not like the square root in A collapse B collapse C, but an A-B preparation may just be a more natural pairing in the apparatus context than the BC measurement. So we do need to consider what is more natural in a particular case, but we need to be systematic in whatever we do if we want to be able to predict the results of experiments in the future. But here I suggest, because it's non-associative, we have what I'm calling a Heisenberg bracketing ambiguity. There's much more than just where the cut is. There's a question of many, many cuts provided by the bracketing. So if we're doing signal analysis, where we have many measurements, we have this, where we have many, many operators that do not commute, giving us a probability, joint probability because of the collapses. whereas we could just use M1 prime through Mn prime and give us the same result. It's not difficult to set both of those up. And we can think of this as Bohr's ideal of a classical model for compatible measurements. And indeed, measurements at time-like separation can give joint probabilities. That's the basis of us discussing autocorrelations in signal analysis. And if you want to do time reversal, then really you need to be a real masochist, I think, to use the collapse version of that because it's going to get enormously complicated. So I'm arguing here that collapse is not only unnecessarily a dynamical process. You can go that way if you like, but we can also take it just to be a joint probability algorithm in which there's no dynamics involved. It's just a matter of producing joint probabilities when we need them. And this is not something that is brand new. You can certainly find it in the literature in various ways, although of course I'm putting a different slant on things. But there's a necessary trade-off here. Quantum mechanics is effective for incompatible measurements precisely because non-commutativity is built into the hardware of the system. But it's rather less good for joint measurements, but we just use collapse to construct joint measurement probabilities when we need to. On the other hand, classical mechanics is rather good for joint measurements because everything is classical unless we introduce the Poisson bracket. It's less good for incompatible measurements, but then we do just introduce the Poisson bracket to give us a way to construct incompatible measurements. So I should really have here a dozen cartoons that say correlation is not equal to causality. But what causal modeling does is, one example, it adds interventions where we have this do notation as a way to discuss counterfactuals. So we put on top of classical thinking, classical modeling, the graphical and logical tools that allow us to do causal modeling. But we have available to us, just within classical mechanics, the Poisson bracket, which gives us a transformation algebra that can model interventions in an intrinsic and classically natural way. I suggest we should just use that. Although not to say you shouldn't use these, it's just that this tool is also available. And it seems to me that we've been talking about measurement incompatibility in terms of contextuality, but it's useful, hopefully, also to think of it in terms of intervention. And this is as much as I have to say about this. This is throwing an idea out rather than being a complete discussion, one slide. Because I do want to talk about the rather simple-minded way I have of thinking about quantum fields, in which we just say that the vacuum state of a quantum field is a broadband, many, many frequencies, many, many wave numbers, noisy carrier signal for probabilistic modulations of measurement results. This isn't your ordinary field theory. So we can construct for a free field the probability distribution for an F measurement just comes to this as a characteristic function. And so as a probability distribution, taking the inverse Fourier transform, we obtain this. So the inner product between F and itself determines the variance of the measurements associated with the F measurements. Now we can modulate the state by using a G modulation, or instead of calling it a G measurement, call it a G modulation, wrapped around this F measurement generating operator to give us this probability distribution, which is just the same as what we have for the vacuum state, except with a displacement, which is determined by the inner product again. So the inner product determines how a G modulation will affect an F modulation wherever those are in space and time. And then finally, what I'm going to call a once-raised modulation, but you're used to calling a one-particle state, we use a G measurement bracketed around an F modulation generating operator to construct a characteristic function. And I've omitted this because it's complicated enough. I don't want to explain it all. But it gives us this two-headed probability distribution. So we've modulated the probability distribution. We've not modulated in a simple way, the way we would with a coherent modulation. We've modulated the probability distribution. And by using more complicated modulations, we can make sure that the F measurements vary in different ways according to what the modulation is. So We can also modulate joint measurements. So we can have F1 modulate measurement, this generating function operator, and multiple such things. And I'm going to call this a super characteristic function because if the F measurements do not commute, then it won't generate for us a probability distribution. It will generate for us something like a Wigner function. Now, all of this is for local measurements. If we want to analyze global properties, which are things we can't actually measure, but it's nice to know about, then we need global tools, and those will have a discrete spectrum, as we see for things like the Hamiltonian operator. So the reason I introduced the super characteristic operator function is because if we state what its value is, we can completely fix the algebraic structure with just one equation. This says that for a Gaussian state, this is the Gaussian noise term that we get generated for this multiple joint probability distribution generating thing. And then as well, though, we have this term, which determines what the non-commutativity is. So this expression is in fact the commutator between an Fi measurement and an Fj measurement. And that turns up in the expression, of course. Now this rho v is a state just if this is a positive semi-definite matrix. That's all that's necessary for this to be a statistical state. So that fixes the algebraic structure. We can also we can fix the geometric structure in multiple ways. We can, for the Klein-Gordon field, we project to the forward mass shell for different wave numbers. For quantum optics, though, we project to the forward light cone. And now we have a bivector test function, which we use to construct two space-like 4 vectors. And now this is also a positive expression, positive inner product it gives us. Now, both these constructions are manifestly Poincare invariant. And that means that we can construct a Whiteman field with what we've just presented here. It's obviously rather different from textbook presentations of free quantum fields. But now we can just remove the theta k0, and that gives us an everywhere commutative Gaussian QND field with a Planck scale noise. And because we've taken out the theta k0 here, that results in this non-commutativity term vanishing. So we're left with just a Gaussian noise for this particular Gaussian state. It's a Gaussian state. So I want to show you how the quantum optics in particular, it can be associated by isomorphism with a quantum non-demolition field theory. To do that, I'm going to introduce lowering and raising operators. So I'm going to write the F measurement in terms of lowering and raising operators that satisfy this commutation relation using exactly the same inner product as we had on the previous slide, and where the lowering operator annihilates the vacuum vector as usual. And that gives us that the commutator between F and G measurements is just exactly what we had on the previous slide. So for the quantum complex Klein-Gordon field, and for quantum optics in particular, we can find what I'm going to call the golden bullet involution. Because it's an involution applied twice, it gives us back the same function. And for that, we insist, what we want to arrange and can arrange is that this expression is 0. And that allows us to use the golden bullet to construct a QND F measurement operator that's not the same as an F bullet measurement. With this construction, we do find that the QND F and G measurements do commute. And so they generate a quantum non-demolition field. And indeed, the Hilbert spaces of these two systems are isomorphic because we've used the same raising operators acting on the same vacuum vector. It's an isomorphism of Hilbert spaces. So the algebra generated by the QND F measurements is not isomorphic, however, to that generated by the F measurements, because of course this is not the same as this. But for quantum optics, I can show you precisely what this, a particular example of this golden bullet. We take the two holistic projections applied to the bivector field test function, and for one of those holistic projection components, we reverse its relationship with the wave numbers in this precise way. Now that golden bullet is Lorentz invariant, but it's not translation invariant or local. but both the quantum and the quantum non-demolition field theories are Poincare invariant. So this makes it rather different from the Broglie-Bohm construction, it seems to me, in this particular respect. So we have that the F measurements and the QNDF measurements don't generate isomorphic algebras, but if we allow ourselves to use the vacuum projection operator, then adding that in gives us two isomorphic algebras. Anything we can model with quantum optics plus the vacuum projection operator, we can also model with QND optics and the vacuum projection operator. So, of course, the vacuum projection operator is non-local because it doesn't commute with any of the F measurements. But in quantum optics, we always use the vacuum projection operator to work with experiments. We're forever using state transition probabilities and so on. So this is something that I find it unlikely we would deny for someone who wants to use QND optics, if that's a useful thing to do. And this is, of course, a classical sort of construction, but there's a Poincare invariant noise. So that makes it non-classical, if you like, but on the other hand, it still is classically comprehensible. So finally, to look at the Whiteman axioms as a precursor to considering how we can think about interacting quantum fields, where we just don't have any in 3+1 dimensions, despite the Whiteman axioms being, to my mind, very simple looking. The Hilbert space supports a unitary representation of the Poincare group. There's a vacuum vector. Quantum fields are operator valued distributions. So I'll say that they are linear maps from the test function space into the measurement operator space. Quantum fields can be a scalar or a vector or bivector or whatever you will. Microcausality insists on commutativity at space-like separation. And completeness just says that the action of the quantum field on the vacuum vector generates the Hilbert space. But thinking in terms of quantum non-demolition field theory and signal analysis suggests at least three ways in which the Whiteman axioms are too strong. We should allow the vacuum to be not a lowest frequency state, since it isn't for a quantum non-demolition field theory. We should allow commutativity at all separations, because that's not satisfied for QND-FT either, and yet there's isomorphisms between these things, so long as we're willing to be open-minded enough about the construction. Finally, and this is what I'll focus on, we should allow, I think, quantum fields to be nonlinear maps into the algebra. So this map should be allowed to be nonlinear. And I want to argue for that in terms of signal analysis. Now, first of all, though, it's implicit in the Whiteman axioms that there are actually two linearities. We have the von Neumann linearity of the state, which I don't want to mess with because that's associated with the probability interpretation of quantum mechanics and quantum field theory. But there's also linearity of the field, where if we take a linear combination of two test functions, then we expect this condition to be satisfied, linearity. But in signal analysis, if we double the amplitude of a modulation, we generally don't expect that will double the effects of that modulation, at least not with the certainty required for linearity to be axiomatic. We should be considering the case in which the equality is not satisfied. Now, I also argue, and this is in this article, which is currently being considered by J. Fizet, doubtless to be rejected next week or whatever, that renormalization is all about renormalization scale, and that it determines the effective dynamics. But that is also determined by experimental details. So we look at an experiment and we decide whether it is acting at the nuclear scale or the atomic scale or at the Higgs scale and so on. But that is something that test functions also tell us. Now, this is too quick an argument, but nonetheless, what I think is the case is that this really does result in us not having as much confidence that this linearity should be axiomatically insisted upon. And for real space renormalization, we have a similar sort of argument, slightly different because there is considerable differences, that the non-trivial blocking algorithms are nonlinear, and so we really shouldn't expect linearity in our quantum fields. So, time. I'm going to take it that I have 5 more minutes. What the Riesz-Schlieder theorem says for a Whiteman field is that local operators acting on a vacuum vector can approximate any vector. But that's what path integrals do. If we have a Feynman integral, we have 4 different regions in which we wish to do measurements, then the Feynman integral computes many loop integrals for many trajectories. And of course, this is a huge calculation, talks about many trajectories, effective trajectories and splittings and so on, and recombinations. But now we can look at the same test functions and say, well, I can construct something that has the same effect as that, because we can approximate the effects of these test functions on the vacuum vector using this. I'm not explaining this as well as I'd like to. But I can think of this as an inverse problem, where we find local nonlinear fragment functionals and free field quantum field theories for which this does give us the same result as this. Now, I don't think of this as the last word. All I hope that it does is that it gives us a sufficiently different perspective for someone else to come along and say, well, oh, maybe I can do something better than that because I now can see what we were doing in this. And this is mathematically well defined, where this is not. As we well know, renormalization is a trouble for philosophers, at least, even if not for many physicists. And finally, I want to say that because we have loosened the Whiteman axioms, of course, we have now more models. So I suppose that tables and chairs, because we've introduced nonlinearity as well as dispersion, can be modeled, hopefully, as something like a caustic. So I think I'm going to not discuss this for the sake of time. It's mostly an attempt to summarize what was in the previous one, because I do want to talk about this as a final generalization. If we're given measurements in which we describe the measurements using description 1, description n, then all we need, so we can construct a Gaussian state over that collection of measurements, is a positive semi-definite matrix, description I, description j. That is a matrix. And that matrix doesn't have to be linear in description I and description j. This is more general than the Whiteman axioms in that respect. And then the domain and the manifest symmetries of that matrix fix what the theory does, fix its relationship to things like space-time and so on. For interacting fields, we introduce and we combine many such matrices, while ensuring that the supercharacteristic function satisfies the requirements for it to be a state, which is both not easy and also much easier in this sort of generating functional way than the Whiteman functions are for the Whiteman reconstruction theorem. And then for gravity, in this perspective, what we have to do is we have to find a way to describe how we measure the geometry of space-time in some idealized way. We don't want to be saying, well, we're sitting in a chair right now and we're measuring the gravity and just have a long-winded description, because we can't do mathematics with that. And then rather glibly, it seems to me that if h bar appears non-trivially in the construction of those matrices, then it's quantum. As I say, this is just a different way of thinking about it, because I feel that we now have some understanding of a different relationship between quantum and classical than the quantization that we have taken to be the relationship for so long. So, final slide. Quantum and classical plus, or QND. The reason I've been talking in terms of QND is precisely to say that this is actually contained within quantum theory. The QND construction is not classical plus, it's just a different way of thinking about quantum. But yet it is classical as well. But they're types of description. So it's not that there are different types of system, because any system can be described classically, classical plus, or quantumly. We shouldn't be saying, oh, this computer is a quantum computer, this computer is not a quantum computer. It's just that we're describing them in different ways. Instead of collapse of the state, we can use the quantum non-demolition picture. But when necessary, we use non-commutativity to model intervention and causality, or contextuality, or measurement incompatibility, whatever you want to call it. And finally, signal analysis suggests the introduction of nonlinearity into the Whiteman axioms. This is where my heart is, really. This is what I've been working on for the last 25 years. And quantum and classical, it seems to me, have been converging, and I'm just trying to channel that in my own particular way and making my own mistakes. And hopefully some of the this way of thinking will resonate with some of you. Thank you very much.